Now let us look at the unit impulse. So this is the simplest of signals that you can think of. So this is using this notation similar to what was followed in the continuous time case. So this is 1 when n equal to 0 and 0 when n is not equal to 0, and the picture that is associated with this is like this. At n equal to 0 it is 1, at for all other points it is 0. And this is the unit impulse sequence in the discrete time case. And one of the things that happens when you multiply an arbitrary sequence x of n with delta of n, what it does is you are going to multiply this delta of n with an arbitrary sequence. At every other point, namely when n is not equal to 0, delta of n is 0, therefore the product is 0. So this is what you get at every other point. At n equal to 0, you will multiply x of 0 with 1, therefore this sample value corresponds to x of 0, and therefore really what happens here when you multiply x of n with delta of n is x of 0 times delta of n. And one common mistake that can be done if you are not careful is this is not x of 0, alright, because if you call this as y of n, y of n equals x of 0 means y of n is the constant sequence whose value is x of 0 for all n, whereas what is happening here is you have to get the value x of 0 only at n equal to 0 and not that value at other points. Other points the value has to be 0. To signify that, you need to multiply this by delta of n, which makes the product go to 0 at other values of n. Similarly, the shifted impulse is delta of n minus n naught, and the picture associated with this is this is n naught, it is 0 everywhere else, and here I have shown the picture assuming n naught to be positive. And similarly, by the same argument, if you multiply this shifted impulse by an arbitrary sequence, it will pick out only the sample at n equal to n naught. So this will be x of n naught times delta of n minus n naught, not just x of n naught by itself, because that would make this to be a constant sequence whose value is x of n naught for all n, which is not something that we want when we do this operation. And this is called as the sifting property. It sifts out that particular sample. So this unit impulse is an extremely simple minded sequence. It is even simpler than the unit step sequence that we saw, and under normal circumstances we should have introduced the discrete time impulse first and then the unit step sequence, but now our goal is to compare and contrast each elementary signal with its continuous time counterpart, and from one extreme of being the simplest sequence, the counterpart we are going to encounter to be the continuous time delta function, which is really a complicated function. So now let us revisit the continuous time delta function. You might think, this being a digital signal processing course where we are dealing with only sequences, why should we care about the continuous variable impulse? The reason why we should is this will appear in the transform domain. So, the continuous variable impulse will appear in the transform domain. So, there is no escaping from this crazy function. So, now let us try to get a feel for what that is. So, this is the continuous time impulse, and this is called as the delta function delta of t, and this is also called as the Dirac delta function after it was introduced by Dirac in quantum mechanics. But this idea of impulse was known even before Dirac's time. So, it is not that he was the one who invented this. He came up with this definition, used it and got the correct results that was completely against what the mathematicians were used to at that point in time. So, since he got the right results, they could not argue against it, but they could not explain it based on whatever knowledge they had. So, the theory of delta was built much later. So, let us first get a feel for this. So, this is t, this is delta of t, and the unit delta function is plotted like this in terms of picture. Its height, whatever that means, is 1, and what we really mean by this is we imply that the area is 1. For the unit impulse, the area is 1. This is not the delta function. Here is a function that takes on the value 1 at t equal to 0. Therefore, coming back to the impulse, delta of 0 being 1 is wrong. Okay. Now, as far as this function is concerned, the one on the right, what is its area? Zero. Okay. I mean, a few people are piping up 0 somewhat hesitantly. Okay. So, area is 0. Okay. Now, more voices are getting added. Very good. All right. So, the area is indeed 0. So, delta of 0 being 1 is wrong. Then what is delta of 0? Not defined. Okay. Any other choices? Infinity. Infinity is a good number. Okay. Infinity. All right. 0 also is a very good number, by the way. But except when it appears on your test paper, it's a profound number. So, delta of 0 is infinity. Okay. We are not sure whether this is indeed true. But what we are used to in terms of delta function is this. That is, the definition that you will find most common in engineering textbooks is delta of t is 0 for t not equal to 0, and then minus infinity to plus infinity delta of t dt must be 1. So, this is the unit impulse. Okay. And the picture that we associate with this in engineering textbooks typically is this. We have a sequence of pulses. So, this is goes between minus delta by 2 to plus delta by 2, and the height is 1 over delta. And then we let the pulse become skinnier and skinnier and taller, all the while maintaining unit area. Therefore, as the limit cap delta tends to 0, the limit of x suffix cap delta of t tends to the unit impulse. So, this is the picture that we have of the delta function. And when you look at the delta function from this viewpoint, it indeed seems that delta of 0 must go to infinity, right. It is infinitely tall, infinitely thin, area is 1, and this is what the delta function is as what we are used to. Because delta of t is defined by these properties, here is another sequence. So, let me call this as y delta of t. Again, limit cap delta of tending to 0 of y delta of t must tend to, the area is again unity, as you can see, half times base times height. So, area is unity. So, this must tend to the delta of t. Any other function that you can give an example that tends to delta of t along the lines that we have just now looked at? Gaussian, yes, Gaussian is very good. So, as the variance of the Gaussian PDF becomes smaller and smaller, the height becomes larger and larger at the origin, area is always 1, therefore, that is also a perfectly valid sequence. Anything else? Hint is signal and its transform, continuous time Fourier transform, your rectangular pulse, right, its transform is sinc. If the pulse width becomes larger and larger, in the limit the pulse becomes the what signal? No, the pulse becomes the single rectangular pulse. If the bit becomes larger and larger, it becomes the DC function, and its transform must be the impulse. Therefore, you have a sinc in the transform domain that is going to become like an impulse, right. So, that is another function that becomes as an impulse in the limit. Now, let us look at this triangular pulse we now saw, right. This, let me take that and cut it into 2 halves, and then cut it in the middle into 2 halves, and then rearrange it like this. Let me call this as z delta of t. What is z delta of 0? Zero. Z delta of 0 is 0 for all delta, okay. Therefore, limit cap delta tending to 0 of z delta of 0 is very good. What is the area of z delta of t? 1, alright. As cap delta becomes smaller and smaller, in the limit as cap delta tends to 0, what does z delta of t tend to? What can you say about z cap delta of t in the limit for t not equal to 0? Z cap delta of t in the limit as cap delta tends to 0, what can you say about the limit for all values of t that is not 0? No, I am just limiting myself to the question of what is the value of the limit for t not equal to 0? Zero, right? And what is the area? So, what does this tend to? Tends to delta of t. But z delta of 0 in the limit is 0. Okay. So, now you see the paradoxes that come into play once you have this kind of reasoning and picture that you are commonly used to when you encounter delta in the usual engineering textbooks. So, okay, all this was kind of done to tell you that the picture that we have z delta in terms of limits of sequences can give rise to all kinds of paradoxes. Okay, on that intriguing note, let us end today's lecture.